This project introduces a concept for an on-site hydrogen production refueling station powered by wind energy, featuring 3 high-pressure storage tanks arranged in a cascade configuration. The system comprises a horizontal axis wind turbine for generating power, an alkaline electrolyzer responsible for hydrogen production, a storage system to maintain the hydrogen at elevated pressures, and cooling mechanisms employed to regulate the hydrogen's temperature increase. To examine the system's dynamic performance, a TRNSYS model is created which will be introduced in this video. On-site hydrogen production fueling stations offer several benefits for a sustainable energy future. They enable decentralized production, reducing transportation costs and dependence on centralized distribution systems. On-site production also enhances resilience, ensuring a continuous hydrogen supply. These stations can utilize diverse renewable energy sources, promoting clean energy integration and reducing greenhouse gas emissions. One of the main challenges of this design is for the refueling station to produce and store the hydrogen to meet the demand of a station throughout the whole year while keeping the hydrogen in a specific range of temperatures. According to SAE J2601 protocol, the hydrogen refueling temperature should be between -40 to 85 degrees, with the gas temperature in the inlet of the cylinder recommended to be within the range of -30 to -40 degrees. Assuming 200 kilograms of hydrogen produced per day, this figure shows the percentage of the total fuel dispensed per day, in the different hours of the day. TRNSYS 18 is used for modeling the system. Now let's dive into the project. The electrolyzer serves as the central component of the system, utilizing the power generated by the wind turbine to produce hydrogen. In this project, an alkaline electrolyzer is chosen for this purpose. The TRNSYS 18 software offers 3 primary temperature modes for the alkaline Type 160A electrolyzer. The first mode takes the electrolyzer's temperature as an input, while the other 2 modes calculate the temperature using either a simple quasi-static thermal model or a more complex lumped capacitance thermal model. The key characteristics of this component are outlined in this table. Data from an alkaline electrolyzer manufactured by Nel Company is used for modeling the electrolyzer. The specifications are detailed in this table. The related connections are as follows. The hydrogen production rate is connected to the buffer tank. The electrolyzer voltage is connected to the output voltage of the power conditioning unit. An auxiliary cooling rate is also supplied to the electrolyzer cooling unit as the required cooling rate for the electrolyzer. Using an iterative approach, Type 175, power conditioning unit determines the necessary current for the electrolyzer by considering both the voltage of the electrolyzer and the power generated by the wind turbine. In this project, the first mode is employed, assuming that the power is provided as input. The value of the output current is presented to the electrolyzer as the electrolyzer current. Type 100A electrolyzer controller is employed to manage the operations of an electrolyzer linked to a wind turbine. The control unit is configured in Mode 1, wherein the desired power output is determined by taking the higher value between the excess power generated by the wind turbine within the minigrid and the power consumption of the electrolyzer when it is in idle mode. Additionally, the controller receives information about the storage level of the hydrogen tank, which stores the gas produced by the electrolyzer. The electrolyzer, along with its cooling system, is activated when the state of charge of the storage tank drops below 0.7 and is deactivated when the state of charge exceeds 0.9. Moreover, the electrolyzer has a minimum allowable idling power of 5000 Watt. The electrolyzer control signal is connected to the electrolyzer and the cooling tower inside the electrolyzer cooling unit. The power set point is also supplied to the power conditioning unit. Weather data is supplied to the system with Type 15-2 components. The city of Kerman in Iran is used as the location for this study. Weather data is given to the electrolyzer, the cooling system for the electrolyzer controller, and the power supply unit, which will be presented later. The connections are as follows. Dry bulb temperature is supplied to the electrolyzer. Dry bulb temperature, humidity ratio, relative humidity, and atmospheric pressure are supplied to the Type 510 cooling tower, located in the electrolyzer cooling unit. Finally, dry bulb temperature and wind velocity are supplied to the Type 90 wind turbine in the power supply unit. Also, the value of the atmospheric pressure is first converted from the atmosphere to Pascal and then connected to the barometric pressure of the turbines. The electrolyzer cooling unit is made of two main lines of flow. The upper line flow is in touch with the electrolyzer and gets cooled in the Type 5A heat exchanger and repeats the cycle. The lower line flows through the Type 510 cooling tower to cool down and returns to the heat exchanger. Type 3D pumps are used for both lines, and an equation component is present to calculate the temperature of the fluid after cooling the electrolyzer based on the cooling rate previously dictated by the electrolyzer and the source side fluid inlet temperature. The flow rate is a constant value of 2 kg per hour. The characteristics of the components are as follows. Load side outlet temperature and flow rate of the Type 5A heat exchanger are connected to the inlet flow of the cooling tower. After cooling down, the outlet flow is connected to the pump and then connected back to the heat exchanger as the load side inlet temperature and flow rate. The source side outlet of the heat exchanger is connected to the previously discussed equation component. The flow is then passed through a pump, similar to the lower line of this unit, and then connected back to the heat exchanger as the source side inlet temperature and flow rate. The selection of the appropriate wind turbine involves a trial and error approach. Initially, the model is run for an entire year to determine the power required by the electrolyzer to meet the demand. Based on this power requirement, a horizontal axis wind turbine is chosen from Vestas catalogs. For this project, this table presents the key characteristics of the selected turbine, a 100 kW turbine costing approximately $43,000. The evaluations indicate that this turbine aligns well with the electrolyzer's demand. The power curve, shown in this figure, plays a crucial role in determining the wind turbines and their primary characteristics. It provides insights into the power generated by the turbine at different wind speeds. Notably, the turbine produces no power when the wind speed falls below 5 meters per second or exceeds 25 meters per second, referred to as the cut-in and cut-out speeds, respectively. The specifications of the wind turbine are altered manually in the external files section of the Type 90 turbine. 3 turbines are set up to provide the system's required power. To address the intermittency issue and make wind power more reliable, one solution is to store the electricity generated during periods of high wind speeds for later use. This can be achieved through the use of energy storage systems, such as batteries. Batteries play a crucial role in smoothing out the intermittency of wind power by providing a buffer between the variable nature of wind generation and the electrical grid. They help to balance the supply and demand dynamics by absorbing excess power and releasing it when needed, thereby providing a steady and continuous flow of electricity. In the present study, the power generated by the wind turbine is compared to the power consumed by the electrolyzer, pre-cooling units, and compressors. If the turbine's power output is insufficient to meet the system's energy demands, the required power is sourced from the battery. Type 2D6 controller is introduced into the system to regulate the connection between the wind turbines and the battery. When the state of charge of the battery falls below 0.8, the power produced by the turbine is utilized to recharge the battery. Once the state of charge surpasses 0.8, the controller disconnects the turbine's power from the battery, allowing the surplus power to be sold back to the grid. This figure shows a visualization of the control functions from the controller. If the turbine fails to generate sufficient power to charge the battery, Type 2D5 controller is implemented that monitors the battery. When the battery's state of charge drops below 0.2, the controller prompts the acquisition of required power from the grid for battery charging purposes. As the mini-grid component in TRNSYS only calculates power discrepancies without providing any power back, a diesel engine is introduced as an alternative power source in the system. Metaphorically acting as a grid, the diesel engine replenishes the battery when the wind turbine's power proves insufficient. Its primary purpose is to utilize the available grid capacity and monitor the power requirements of the system. The controller disconnects the battery from the diesel engine once the battery's state of charge exceeds 0.8. This figure shows a visualization of the control functions from the controller. After executing the TRNSYS code and analyzing the system's consumption, the specifications of the diesel engine are chosen accordingly. The findings indicate that the highest recorded consumption amounts to 8 kilowatts. Consequently, a rated power of 8.5 kilowatts is selected for the diesel engine, ensuring that the necessary power is adequately supplied to the system. In this project, the surplus and deficit power values mentioned above are stored as positive and negative values, respectively. These values are subsequently graphed to depict the amount of power sold to the grid and the amount of power consumed from it. The power output from the turbine is connected to the equation 6 component, as well as the output control function from the Type 2D6 component. Equation 6 will calculate the product of the two inputs and connect the result to the control equation. The state of charge from the Type 47 battery is connected to both of the controllers as the lower input values. The load equation component calculates the total load of the system, including the power consumption of the electrolyzer, hydrogen compressors, and cooling systems. The load power is connected to the control equation in the power supply unit. The fluctuations in hydrogen production necessitate the storage of the generated hydrogen in high-pressure tanks. To mitigate fluctuations at the compressor inlets, a buffer tank is employed. This buffer tank allows the hydrogen to be compressed from the buffer tank to a low-pressure storage tank and subsequently to the high-pressure cascade system, as depicted in this figure. The key parameters of the buffer tank and pressurized tanks are outlined in this table. The low-pressure master control equation component has two main purposes. This equation receives the volumetric rate of hydrogen consumption per hour. This value is multiplied by 2 and then used as the volumetric flow rate of gas entering the compressor, as suggested by this article, which found that the optimum hourly capacity of the compressor is approximately twice the station's average hourly demand. Finally, this equation component receives signals from Type 2D 3 and 4 components. If both signals are equal to 1, an on signal is sent to the low-pressure compressor. Otherwise, the master controller will signal the low-pressure compressor to turn off. The resulting signal is also given to the low-pressure cooling system, which is similar to the electrolyzer cooling unit. The Type 2D3 controller is used to maintain a sufficient amount of hydrogen within the buffer tank. For this purpose, the pressure level of the buffer tank serves as the upper input value for the controller. Meanwhile, the lower input value is established at 0.6, accompanied by an upper deadband value of 0.1 and a lower deadband value of 0. These settings ensure that the pressure level within the buffer tank remains consistently between 0.6 and 0.7, guaranteeing an adequate supply of hydrogen in the tank. As a result, this controller sends an on signal to the master controller, if the pressure level of the buffer tank exceeds 0.7, and an off signal is sent if the pressure level falls below 0.6. To keep a sufficient amount of hydrogen in the tanks, the Type 2D4 controller serves a similar purpose to the buffer tank controller. However, it operates based on the low-pressure tank's pressure level as the controller's lower input value. The upper input value is set at 1, along with an upper dead band value of 0.3 and a lower dead band value of 0.1. These parameters ensure that the pressure level of hydrogen within the low-pressure tank remains within the range of 0.7 to 0.9. If the pressure level of the low-pressure tank falls below 0.7, the controller triggers an on signal to activate the low-pressure compressor. Conversely, if the pressure level exceeds 0.9, an off signal is sent to deactivate the compressor. Type 2D controller has the same setting as the buffer tank controller and sends an on signal to the high-pressure master controller, if the pressure level of the low-pressure tank exceeds 0.7, and an off signal is sent if the pressure level falls below 0.6. The Type 167 component, working as the low-pressure compressor, receives the gas pressure inside the buffer tank as an input and gives the volumetric outlet flow to the buffer tank as an input. The volumetric outlet flow from the compressor is connected to the low-pressure tank as the volumetric rate of gas entering the tank. The energy released during the compression is given to the low-pressure compression cooling system. In this project, Type 164 is used for modeling storage tanks. The buffer tank's connection is as follows. The buffer tank's pressure level is connected to the electrolyzer controller and controller 2D3 as the upper input value. The low-pressure tank's connections are as follows. The low-pressure tank's pressure level is connected to controller 2D4 as the lower input value. The gas pressure of this tank is also connected to the high-pressure compressors. The Type 2D, 350, 500, and 700 controllers have the same setting as the Type 2D3 controller and send an on signal to the high-pressure master controller if the pressure level of any of the high-pressure tanks falls below 0.7 and an off signal is sent if the pressure level exceeds the value of 0.9. The high-pressure output equation will calculate the sum of the compressor power, energy released, and volumetric outlet flow from the high-pressure compressors. The energy released from the compressors is given to the high-pressure master controller as the cooling power. The sum of the volumetric outlet flow from the high-pressure compressors is connected to the low-pressure tank as the volumetric rate of gas exiting the tank. High-pressure master control equation. The high-pressure master control equation has the following input signal from the Type 2D controller. The volumetric rate of hydrogen consumption per hour signals from Type 2D, 350, 500, and 700 controllers. The cooling power for the compressors. The source side outlet temperature outputs. This equation will calculate the following. Cascade system signals for compressor signals from Type 2D and each of the three high-pressure tank controllers are compared. If both signals are equal to 1, an on signal is sent to the respective high-pressure compressor. Otherwise, the master controller will signal the compressors to turn off. The volumetric flow rate of gas entering the compressors, equal to the volumetric rate of hydrogen consumption per hour, multiplied by 2. The temperature of the source side flow, returning to the cooling unit calculated from Q equal mc delta T relation, by considering a constant value of 5 kg per hour for the mass flow rate of the source side flow. The high-pressure compressors connections are as follows. The volumetric outlet flow from each of the high-pressure compressors is given to their respective high-pressure tank. High-pressure compressor cooling unit is similar to the electrolyzer cooling unit. The source side outlet temperature is connected to the high-pressure master control as the cooling fluid's inlet temperature. Cooling tower fan control signal is supplied by the compressor signal in the high-pressure control, so is the control signal for the Type 3D 5 and 6 pumps. The mass flow rate and temperature of the source side flow, returning to the cooling unit, after cooling the cascade high-pressure compressors, is also given to the Type 3D 5 component. The temperature of the source side outlet temperature is connected to equation 9 as the hydrogen's temperature after the compression. The specific heat and constant pressure, cooling load and the pre-cooling system's energy consumption is calculated using EES software. In this code, an average temperature of 80 degrees is assumed for the hydrogen. It is also worth noting that the specifications of the refrigeration cycle are determined using an iterative approach. A mass flow rate is assumed for the refrigerant and then by adjusting the final temperature of the hydrogen to be within the desired range, the mass flow rate of the refrigerant is obtained. This table shows the specifications of the compressed refrigeration cycle. A crucial part of the system modeling is the hydrogen demand of the refueling station. The accuracy of this section directly affects the precision of the whole model. The demand is modeled based on the total number of cars that enter the station at each hour of the day. Assuming that each car has a tank capacity of 5 kg and a refueling time of 3 minutes, we can determine not only the total demand of a day but also the mass flow rate of hydrogen. This figure shows the daily demand of hydrogen for the station, where each hour's demand is expressed as a percentage of the total daily demand, which is assumed to be 200 kilograms. Once we have the hydrogen demand for a day, we can estimate it for a week, month, or year by multiplying a constant factor by the reference day. This factor may vary depending on the location and is reported in many papers. For example, we can expect a higher hydrogen demand on weekends due to road trips or short journeys. The first component defines the daily demand and then the other components adjust it for weeks and months accordingly. The equation 2 component calculates the consumption rate of the system per hour. The percent of the total hydrogen consumption per hour is supplied to the equation as the input. This parameter is first multiplied by 200, which is the total hydrogen consumption in a day, and then divided by 46.37, the density of hydrogen, to find the volumetric flow rate of hydrogen per hour. Here are some of the results from this study.